Hey there, Calc 2 crew, and welcome back to the Daily Problem Sets. And for today, we're going to take a look at 7.7, talking a bit about the approximation techniques in our course. And here we're going to talk about midpoint rule, trapezoidal rule, and Simpson's rule. Remember, should have already taken a look at the lecture videos, but otherwise, we're going to go ahead and take a look at some problems together. Let's go ahead and take a look at this very first example that we have. We're just going to do the setup only, and we're setting up to find approximations using all three: midpoint rule, trapezoidal rule, and Simpson's rule. And here we're approximating the following definite integral, the integral from 1 to 2 of the function 9e to the 1 over x with respect to x, and here we're prompted to use n equals 4, so 4 partitions. The very first thing that we want to do is we want to calculate delta x. Delta x is given as b minus a all divided by n. In this case, a and b are the lower and upper bounds on the integral. So we'd say b then is 2, the upper bound, minus a is the lower bound, which is 1. And this is all divided by n. Here n is given, that's 4. Then we compute this. 2 minus 1 gives us 1 over 4 is 1/4, or we could write this as a decimal, 0.25. Once we have delta x, we want to write out our subintervals, and we know that we should have n of these equal spaced subintervals. So I like to write these as, n empty boxes. I like to stack them vertically. And we know that the very first subinterval has to start where the interval starts, which is at 1. And then the very last subinterval has to end where the interval ends, which would be at 2. And the idea is that we're going from 1 to 2, but we're just going to break it up into 4 equally spaced subintervals. Now to fill in the rest, we just have to build right endpoints by taking any left endpoint and adding delta x to it. So for example, in this first subinterval, I take my left endpoint, which is 1, I add delta x to it, so I want 1 plus 0.25, gives me 1.25. But then the next subinterval, there should be no gaps or breaks in this process. Think of it like a road trip broken up. If you stop at the rest stop to get some Doritos or like a Gatorade, like a Riptide Rush Gatorade, then once you resume traveling, you're going to have to leave from that same gas station with the Cooler Ranch Doritos. So here the second subinterval should start at 1.25. And then to complete that subinterval, we add delta x again. So 1.25 plus 0.25 gives us 1.5. The third subinterval should start at 1.5. We add delta x again, gives us 1.75. And then now we can check our work to make sure we didn't make some small error or we didn't skip over anything or double anything up. The last subinterval should start at 1.75. And then certainly if we add delta x to this, it'll bring us to 2. So everything looks good. If you want to break that interval from 1 to 2 up into 4 equally spaced subintervals, you want 1 to 1.25, 1.25 to 1.5, 1.5 to 1.75, 1.75 to 2. Those are the 4 subintervals. Now for midpoint rule, I'm going to need midpoints. So here I want to find the midpoints of each subinterval. I'm going to label these x of 1 bar or so on and so forth. So the first midpoint, if I want to know what's halfway between 1 and 1.25, that's going to be 1.125. And if we can't tell what the midpoint is by inspection, a way that I can compute it is just by averaging the endpoints of a subinterval. If I want to know what's right in the middle between these two numbers, I would take 1 and add it to 1.25, and then divide it by 2, just finding a very small average. So if you're not quite sure, then you can always do that. And then halfway between 1.25 and 1.5, that's going to give me 1.375. And again, if I don't know what that is, I can add these two numbers together and then divide by 2. Halfway between 1.5 and 1.75, that's going to give me 1.625. And then the last midpoint, x sub 4 bar, halfway between 1.75 and 2, is going to give me 1.875. So now we have all these midpoints. Now that I have all my subintervals and all the midpoints, I can go ahead and work through these. Really, it's midpoint rule that's going to need the midpoints. Let's go ahead and work with midpoint rule first. Now, in general, I can sort of write down how the formula would look for midpoint rule. So let's start with midpoint rule. Here I would want delta x factored all the way in front. And then I want to evaluate my function at the midpoints. So generically, I want f at x sub 1 bar plus f at x sub 2 bar plus f at x sub 3 bar plus f at x sub 4 bar. So I'm evaluating my function at the midpoints. I'm summing those evaluations from the function. After I'm done with all the adding, I would lastly multiply by delta x. That'd be the last thing we would do. So let's go ahead and plug in these pieces and see what it is. So here delta x was 0.25. So that's going to be all the way out in front. And this would maybe be a little bit nicer if I had fractions instead of decimals, but that's not what we have at this moment. Next, I want to look at my function. My function f is this function that we aren't integrating, right? In fact, we're using the approximation method in lieu of that. But this is the function when we refer to function f. It's this 9e to the 1 over x. So then I want to plug these midpoints in. So that would be 9e to the 1 divided by 1.25. Sorry, 1.125. And I want to add to this, and I want to plug in the next midpoint, so 9e to the power of 1 divided by 1.375. And keep going, Can't stop, won't stop. 9e to the 1 over 1.625. And then we get to this last midpoint. Plugging that in gives us 9e to the 1 over 1.875. And we just said the setup only. So here we got a really good setup for midpoint rule. Some of these, and this example is a great example of it, some of these require the use of a calculator to really get anywhere reasonable with it. So you'd want to plug this into your calculator, beep, boop, beep, bop, beep, boop, beep. And then you'd want to figure out what the approximation is. Try not to round. The more you start rounding, the more you're truncating the approximation. The approximation is trying to be the best that it can be. So if you start rounding things early on, then you're not really helping out. And if your calculator is willing to give you lots of sort of digits, try to keep those digits. Let me know the digits. But be very careful, right? So there's a lot of opportunities for calculator error. Let me know what you get for this one. Let me know what you're getting. But let's talk about trapezoidal rule. Switch colors. Of course we will. Trapezoidal rule. I won't write down the generic formula. I will write down the formula as it pertains to the example that we have. But the idea with trapezoidal rule is that we don't need to work with midpoints. Midpoint rule is actually a Riemann sum calculating the area under the curve using rectangles where the heights are dictated by the midpoints of the subinterval. Trapezoidal rule actually uses trapezoids, believe it or not. And in this case, we're not going to use midpoints for this. We're going to use endpoints of the subintervals. We refer to these endpoints as f at x sub 0, f at x sub 1, x sub 0, x sub 1. We are going to plug them into f, but we refer to the endpoints as x sub 0, x sub 1, x sub 2, so on and so forth to x sub n. So for us, how our trapezoidal rule is going to look in a generic fashion, it's going to be f at x sub 0. And then next, we want to add to this, we do want f at x sub 1, but I want to multiply that by 2. It should have a coefficient of 2. And I want another coefficient of 2 on all the rest of these until I get to the end. So next would be 2 times f at x sub 2. Next would be 2 times f at x sub 3. And then we would get to the very last endpoint, which would be x sub n. And I want to plug that into f. And I want no coefficient, or here we would say a coefficient of 1. So this formula, I like to describe it as being bookended, since the very first and the very last term inside the parentheses have no coefficient or a coefficient of 1, but then everything else in the middle has a coefficient of 2. And you'll notice that we have, for having 4 subintervals, we actually have 5 of these endpoints. We can actually count them to see. Here we have 1, 2, 3, 4, 5 of these distinct values. And a helpful device to help. A nice way to remember the formula is the values that we plug into the function that get that coefficient of 2 actually appear twice over. So we see them literally twice over if we're writing out the subintervals. But let's go ahead and write out this formula now as it pertains to our example. So here we have delta x divided by 2 in front. And here I would want f at 1, right here, x sub 0 is 1. Next, I would want 2 times f at 1.25. Next, I would want 2 times f at 1.5. Next, I would want 2 times f at 1.75. And lastly, I would want just f at 2. The very first and the very last don't get that coefficient of 2. And any of these values that we see appear twice over get the coefficient of 2 after we plug them into the function. Don't forget our function is this 9e to the 1 over x. So that should be what we're plugging into. And don't forget delta x is 0.25. Here we said delta x was 0.25, or 1/4. So we have 1/2 times delta x. Delta x, I have it as a decimal. Let me use it as a fraction, though. That's 1/4. If delta x is a fraction or a decimal, I should say a proper fraction, with working with something like delta x divided by 2, I like to maybe think of it like 1/2 times delta x, just because I don't want a complex fraction if I can avoid that. And for the rest of the stuff here we have 9e to the 1 over 1, 2 times 9e to the 1 over 1.25, 2 times 9e to the 1 over 1.5, 2 times 9e to the 1 over 1.75, and then here we get to just f at 2 is 9e to the 1 over 2. And we won't go too crazy with this. If I did leave these as fractions instead of decimals, I'd be able to do the reciprocating in the exponent, which I think would be nice, but otherwise, here I can find 1/2 times 1/4 is 1/8. E to the 1 over 1 is e to the first, which is e, so this is just 9e, plus 18e to the 1 over 1.25, plus 18e to the 1 over 1.5, plus 18e to the 1 over 1.75, plus here we have 9e to the 1/2. Well, you can think of that as square root of e if you'd like to. I think this looks good, reasonable. Certainly, if you'd like to, you could factor a 9 out, and you could be doing that with any of these examples, since our function, f, actually has a 9 in the coefficient. But let's go ahead and talk about this last approximation method, Simpson's rule, and let me know what you're getting for these. I'm interested to see what's going on with them. Make sure you can, use the calculator on things like the homework, and make sure you're not getting any calculator errors, so we can certainly check for that. Simpson's rule. There's actually a lot of different variations on the formula for Simpson's rule. The one that we're using for our course is going to be delta x divided by 3 out in front. And then inside the parentheses, we're going to have f at x sub 0 plus 4 times f at x sub 1 plus 2 times f at x sub 2 plus 4 times f at x sub 3 plus 2 times f at x sub 4 plus so on and so forth, plus 2 times f at x sub n minus 2 plus 4 times f at x sub n minus 1 plus a bit of enjambment here, f at x sub n. And hey, this is the most work involved, certainly, but it is going to give us a really good approximation. We have delta x divided by 3 in front, and then here we're just plugging in endpoints with this particular version of Simpson's rule. There is a restriction that we have to make, and I'll mention that in just a bit. But our formula, this one is bookended too. The very first, f at x sub 0, and the very last term, f at x sub n, have no coefficient or a coefficient of 1. But in between, we have this alternating 4, 2, 4, 2, so on and so forth, 2, 4, and then eventually back to 1 kind of pattern. So the coefficients are a little tricky, but we sort of notice a pattern. If I go through and talk about the coefficients, we get 1 for the first coefficient, and then 4, and then 2, and then 4, and then 2, and then 4, and then 2, so on and so forth, until we get towards the end, then we get 4, and then 2, 4, 1. So that's what it's sort of looking like with Simpson's rule. The restriction that we have to place on this version of Simpson's rule that we're using is that n must be even. So we must have an even number of partitions in order for this to work. But let's go ahead and plug in what we have for our specific example. We said delta x is 0.25, or that was 1/4. And here I want 1/3 of that. So I'm just going to write this as 1/3 times 1/4. And then here in the brackets, I want f at x sub 0. Remember, f is still that same function, 9e to the 1 over x. And x sub 0 is 1 in this case. So I want f at 1. So that's 9e to the 1 over 1. And then I want 4 times f at x sub 1. And that's going to be 1.25 plugged into the function. And then I want 2 times f at x sub 2, and that's going to be 9e to the 1 over 1.5. And then next it should be a coefficient of 4. That's 4 times, and it's going to be f at 1.75, so that's 9e to the 1 over 1.75. And then we get to the end, which is plugging in 2, and we have no coefficient, so that's just a function, which was 9e to the 1 over 2, if I plug in 2 for that. So we do have these 9s that came from the function, but otherwise we have coefficients 1, 4, 2, 4, 1. That's how it's looking. And that would be 1, 4, 2, 4, 1 for that crazy alternating pattern that we get. And we're going to leave this one. Let's clean it up just a bit though. 1/3 times 1/4 gives us 1 over 12. And then here we have 9e, plus here we have 36. E to the 1 over 1.25 plus 18 e to the 1 over 1.5 plus 36 e to the 1 over 1.75 plus 9e to the 1/2. And again, let me know what you're getting for these. Be very careful evaluating them, but hey, I want to know. I want to know what you're getting. So let me know. Let's move on to talk about estimating errors for trapezoidal and midpoint rule. There is error that we can estimate for Simpson's rule, but we're not going to take a look at that together. But we will take a look at trapezoidal rule and midpoint rule. We have the following. We say, suppose the absolute value of f double prime of x is less than or equal to k on the interval from a to b on x. If capital E sub t and capital M sub t are the errors in the trapezoidal rule and midpoint rule respectively. Well, I think my notation here is a little bit funny, so you're seeing this in real time. It is the error associated with trapezoidal rule, so E for error, T for trapezoidal rule. For midpoint rule should be error associated with midpoint rule, and I have it correct down here. So, hey, it's going to be a crazy day today. But let's go ahead and take a look at it otherwise. Errors associated with trapezoidal rule and midpoint rule are given by, here the absolute value of the error associated with trapezoidal rule is less than or equal to k times b minus a quantity cubed divided by 12n squared. And then the error in absolute value associated with midpoint rule is less than or equal to k times, we have b minus a quantity cubed divided by 24n squared. So the very first thing that I need to do is I have to find k. And k is some sort of upper bounding that we get on the second order derivative. Okay, so that sounds kind of crazy, but let's see what we can do with this. The examples that we're looking at for this are going to pertain to the previous problem that we just did. So this problem here, because we have to be talking about some problem, some application, and the function that we had, let me actually write down all the information. It was the integral from 1 to 2 of 9e to the 1 over x. So we had the integral from 1 to 2 of 9e to the 1 over x dx, and we were using n equals 4. So that's sort of the important information that we're going to need. And the function that we have, f of x, f of x is this 9e to the 1 over x. Or we could rewrite this as 9e to the power of x to the negative 1. And it's just going to make it a little bit easier for differentiation's sake. Now, if I take the first order derivative, f prime of x, I'm going to need chain rule for this. So we get 9 comes along as the coefficient. Derivative of e to the stuff is e to the stuff. But then I have to multiply by the derivative of the exponent, which gives me negative 1 x to the minus 2. Now from here, if I want to find the second order derivative, I'm going to need more chain rule, but overall I'm going to need product rule. So we'd say f double prime of x. For product rule, I'm going to rewrite this first factor, 9e to the x to the minus 1. The derivative of the second factor is going to give me positive 2, x to the power of minus 3. And then I'm going to add to this. Now I'm going to rewrite the second factor, negative 1 x to the minus 2. I'm going to multiply by the derivative of the first factor. And the derivative of 9e to the x to the minus 1 is just another chain rule. So we get outer derivative and then the inner derivative again. Should look familiar because we had to do that to get f prime. Now I'm actually not going to stop here. I'm going to move on to find the third order derivative. So I'm going to go ahead and clean this up. I'm going to say, let me factor the 9e to the x to the minus 1 out. And then I'm left with 2x to the minus 3 plus, and then negative 1 times negative 1 is positive 1. X to the minus 2 times x to the minus 2 is x to the minus 4. So this is what I get for a cleaned up version of f double prime of x. Now there's a reason why I wanted to do this. I said I wanted to find the third order derivative. So let's move on and find the third order derivative. And here we kind of stop with the prime notation, and we use the superscript parentheses to indicate the order of the derivative. So this means third order derivative. And here I need to use, again, product rule with a chain rule application. So I'd say, let me rewrite 9e to the x to the minus 1. Derivative of the other factor is going to give me negative 6x to the minus 4, and then plus negative 4x to the minus 5. Then I can add to this. Now I can rewrite this second factor, so I'm just rewriting the 2x to the minus 3 plus x to the minus 4 times the derivative of the first factor, which is 9e to the x to the minus 1 times negative 1x to the minus 2. Now there's something that I want to sort of point out about this third order derivative. Let me actually factor and clean up a bit. I'm going to just factor the 9e to the x to the minus 1 out. But then what am I left with otherwise? I have negative 6x to the minus 4 plus negative 4x to the minus 5 plus, if I multiply this in, here I'm going to have negative 1 times 2 is negative 2. X to the minus 2 times x to the minus 3 is x to the minus 5. And then I have negative 1, so plus negative 1 x to the minus 6. And I could go ahead, I could combine some like terms in there. I could rewrite as fractions, but just for the sake of saving on time, let me point out what I want to point out. Every single term here is negative. Negative, 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 negative. And our overall interval from A to B was the interval from 1 to 2, if you remember from the original problem. We said the integral from 1 to 2. So for any of these values for x, I'm always going to get something negative. If I really wanted to, push this idea home and add insult to injury, I could factor a big old minus sign out of all of this stuff and say, look at it, everything's negative. There's that minus sign. But so what I'm trying to say here, let me stick with the baby blue. I want to say that my third order derivative is negative. And that this means my second order derivative is decreasing. Remember, a derivative lets us know some qualitative information about the original function. It might seem a little bit different than what you did in Calc 1, since we're using the third order derivative to describe behaviors of the second order derivative, but that's just a semantics argument. Think of it this way. you call your mom mom, and you call your grandmother grandma, but your mom calls grandma mom. So what I'm trying to say is just the relationship between f double prime and the third order derivative is just a first order derivative between the two. You know what I'm saying? So what we're doing is we're sort of using this kind of cat and mouse derivative relationship to describe the former function. So we'd say since the third order derivative is negative, that means the second order derivative is a decreasing function. So now that I know that f double prime is decreasing, f double prime is maximal at x equals 1 on the interval from 1 to 2. Since my second order derivative is decreasing, then if I want to catch it at its highest, I have to catch it right at the start of that interval. Otherwise, it's going to decrease and it's going to get smaller and smaller and smaller. So I want to find my value for k by finding f double prime at 1. And let's actually rewrite what f double prime of x was. I had it kind of cleaned up, but I didn't really clean it up too much. Let me clean it up a bit more. That's 9e to the x to the minus 1, or I can write that back as 9e to the 1 over x. And then in the parentheses, here I have 2x to the minus 3, or that's 2 over x cubed, plus x to the minus 4. I can say that's 1 over x to the 4th. So this is my second order derivative. And I want to evaluate this at 1. So we'll say, okay, f double prime at 1 is 9e to the 1 over 1 times 2 divided by 1 cubed plus 1 over 1 to the 4th. And that's going to give me 9e. 1 cubed and 1 to the 4th is just 1. So then times 2 plus 1. This is 9e times 3. But this gives me 27e. And this is the value that we're going to use for k. So here we have 27e. 27e. So now we can use this to find the errors associated with trapezoidal rule and midpoint rule. Now we have k is 27e. So okay, so we have these formulas we can work with. Let's do trapezoidal rule first. That's k times b minus a cubed over 12n squared. The error associated with trapezoidal rule less than or equal to k times b minus a quantity cubed over 12n squared. And I can plug everything in. So here I know that k is 27e. A and b, remember, that comes from the interval that we had. So a is 1 and b is 2, coming from the bounds. So that's 2 minus 1 cubed, all over 12 times n squared. And we said n was 4. So 12 times 4 squared. And then here I can go ahead and evaluate this. And we'd say 27e, 2 minus 1 is 1, 1 cubed is 1, divided by 12 times 4 squared. We'd say 12 times 16. And then to talk about this as an error, you know, we could continue on with this. But really what I'd want to do is get some decimal approximation. This is going to give us about 0.3822 for that error associated with trapezoidal rule. So if I'm using trapezoidal rule and I want to know, well, how good is it? How bad could the approximation be? This is going to give me some insight into that. Let's take a look at, alternatively, the error associated with midpoint rule, and this is very similar in its formula. It's just k times we have b minus a quantity cubed over 24n squared. So here we'd say absolute value, the error associated with midpoint rule, less than or equal to, so it was k and then b minus a quantity cubed over 24n squared. And then we can plug into this one as well. So we'd say, well, k is still 27e. b minus a is 2 minus 1. I want to cube that difference over 24 times n squared. and n is 4. And then same idea, 2 minus 1 is just 1, 1 cubed is 1. So here we have 27e divided by 24 times 16. And then this gives us, as a decimal value, this one is about 0.1911 for the error. We'll take a look at one more example. So here I want to use what we just talked about, those error-bound evaluations, to figure out how large would we want to choose n, the number of partitions, so that the approximation for trapezoidal rule and midpoint rule are accurate to within 0.0001. So that's 0.0001. So this is a bit different because now I actually know what I want that error to be. And we sort of think about this as, a single-sided error when we work with it, and we would just plug this into our left-hand side of our formula. There's going to be sort of a bit of discussion that we're going to have with the inequality symbol, since we're not really going to want to treat this as an inequality. We're going to want to treat this perhaps more as a strict equality and still even interpret it after the fact. But just for jotting it down, I am going to write the inequality symbol. Shouldn't hopefully be too bad. But the error associated with trapezoid rule, let's say I wanted this to be within 0.0001 and less than or equal to, and then here I can fill in all the rest of the stuff that I know. We said k was 27e, and then b minus a was 2 minus 1 cubed, and then divided by 12n squared. But I'm leaving n as n because I'm saying, well, what if I don't want just 4 partitions? In fact, how many partitions should I select so that the error is accurate to within 0.0001? So here I'm leaving n as n, and I'm trying to actually solve for it. Okay, so we go ahead with this. Let's say here I have 0.0001. And then I can multiply the 12n squared over. Why not? And then less than or equal to. And then here I have 27e times 1 cubed, which is just 27e. And if I want to multiply the 12 in, that's going to give me 0.0012 n squared, less than or equal to 27e. I can divide by the decimal number, so n squared less than or equal to 27e divided by 0.0012. And then I would just want to take the square root. So then n less than or equal to the square root of 27e divided by 0.0012. Now taking the square root gives me this value that I can work with. This should be about 247.308. But we have to interpret this, and we have to think about what this means and sort of disregard the inequality symbol. It doesn't make sense to say n is less than or equal to this, because as n gets smaller, the approximation actually gets weaker. So think of it this way. What we've just said is that for trapezoidal rule, if I want this approximation to be within 0.0001, then I would need exactly 247.308 partitions in order to guarantee that. Since I can't have 0.308 of a partition, I really should always be rounding this up. I have to round up just to make sure that I'm having enough. If I start rounding down, that might not be good enough. So we'd say, yeah, we round this up, so we'd say 248 partitions is what we need. That isn't to say that we couldn't maybe get away with fewer partitions, but in order to guarantee it without actually going through the work and comparing against an exact value, in order to guarantee it sight unseen, I would need 248 partitions in this case. And then we can go ahead and do the same working with our midpoint rule. Similar computation, and we're still saying that we want the error to be this 0.0001. So we'll just do this one very briefly. That'd be 27e, 2 minus 1 cubed divided by, now this is 24n squared. Now I can multiply the 24 n squared over, so that gives me 0.0024 n squared less than or equal to 27e. And then I can divide by the 0.0024, so n squared less than or equal to 27e divided by 0.0024. And then I want to take the square root. And this gives me, for a value, gives me about 174.873. And again, we'd say, so what this is telling us is that we would need about 174.873 partitions for this to be exact. However, I can't have 0.873 of a partition, so I have to round this up. I have to round this up and say that I would need 175 partitions. And this would be to guarantee, to promise you the indicated error before even doing the computation. Could it work with some smaller amount of partitions? Maybe. But can I promise it to you? I won't be able to promise it. So this is something that we can promise before even doing any approximation method. I can look into this and say, well, if I know I need it to be accurate, then I know how much work I would have to put in, right? All right. Well, so that's it for 7.7. Let's go ahead and take a look at the material for 7.8, talking about improper integrals. And let's go through a few of these examples. So I want to determine whether the improper integral is convergent or divergent. And the very first thing that I want to do in all of these cases is rewrite into the limit of a proper integral. So this first example, the integral from 0 to infinity of 8 sine squared of x dx, it's no good. Infinity should not be a bound. It's not a number. So instead, I want to write this as the limit as our dummy variable t goes to infinity, the integral from 0 to t of 8 sine squared x dx. So I use this placeholding variable, and make sure you're doing this. Notation is everything here. Let's talk a bit about integration. To integrate sine squared, this is a trig integral, I have to use an identity. And I want to replace sine squared with 1/2 quantity 1 minus cosine 2x. And I can integrate this identity. So this will just be my work in the margin. I'm saying notice, and I'm doing the integration here in a generic sense. 1/2 comes along for the ride. If I integrate 1 with respect to x, gives me x, minus, if I integrate cosine of 2x, gives me sine of 2x divided by 2. I could really use a substitution to show that work. And then just as an integration in general, I would say plus c. But I don't plan on using this as an indefinite integral. I actually have this improper integral that I'm computing. So I'd say, well, I can use this result here. I have my work for it. So this is the limit as t goes to infinity of, and here I have 8 times 1/2 times in parentheses x minus sine of 2x over 2. I don't need the constant anymore, and then this is evaluated from 0 to t. Now I want to keep this limit notation, but I'm ready to work through the fundamental theorem of calculus part 2. So here I have my limit as t goes to infinity. And here I have 8 divided by 2 is going to give me 4. And I'm going to leave this kind of factored out in front. I could bring it in front of the limit notation as well, though I won't. And then I can go ahead and plug in my upper bound and my lower bound. When I plug in my upper bound, I get t minus sine of 2t over 2. And then minus, I subtract away from this. When I plug in 0 for x, I get 0 minus sine of 0 divided by 2. And I can evaluate this as much as I can before I take the limit. So we'll say limit as t goes to infinity. I have 4 times. I can't do anything with the t terms yet. That's t minus sine of 2t over 2. But the rest of these terms, 0 is 0, so that's gone. Sine of 0 is 0. 0 divided by 2 is 0. That's gone. So I really just have minus 0, which means I'm really just left with this upper bound evaluation. And now I really don't have anything else to do other than to talk about these limits. Now, the first one is really just sort of an identity function, right? Limit as t goes to infinity of t. Well, as t goes to infinity, what does t do? T goes to infinity. Almost seems like it's a bad joke. Where's the punchline? So the limit as t goes to infinity is infinity. What about this other piece, though? Now let's talk about sine of 2t. The limit as t goes to infinity of sine of 2t. What would you say about this? Let me know in the comments below. What would you say about this? Say this limit does not exist. And in fact, what happens here with the sine function as t goes on is it just keeps doing what the sine function does, which is this oscillation. Right? So here we have this oscillatory behavior. So it doesn't settle on anything, right? It sort of goes through a range of values over and over again in this repetitive, predictable kind of way, but it never reaches anything. It never agrees on anything. It never settles anywhere. So we just have this sort of oscillating behavior. So when we think about what this gives us for a final answer, we'd really be sort of stuck saying that the limit doesn't exist. Here we have infinity minus something that oscillates. So we would say, okay, so then limit doesn't exist, and this means that what we have is divergent. So here we have a divergent improper integral. Let's take a look at another one. Here we have the integral from 2 to infinity of 1 over x squared plus 8x minus 9. And remember that very first step, we want to write this as a limit of a proper integral. Limit as t goes to infinity, the integral from 2 to t of 1 over x squared plus 8x minus 9 dx. Now to integrate this, we're going to need to work with partial fraction decomposition. So I'm going to go here to the side and I'm going to do some scratch work. If I factor this, we should get x plus 9, x minus 1. And this is a case 1 partial fraction decomposition, so I can do a over x plus 9 plus b over x minus 1. And I can build back the common denominator, multiplying the a over x plus 9 by x minus 1 over x minus 1, the b over x minus 1 by x plus 9 over x plus 9. And then I can work with the numerators, and I can say, well, then 1 should be equal to a times x minus 1 plus b times x plus 9, or that 1 is equal to ax minus a plus bx plus 9b. And I want to set like parts equal. So if I look on the left-hand side, I don't have any x term, so it would be a 0 from the 0x. Now what about the x's on the right? Well, I have an ax and a bx, and I just want to work with the coefficients, so a plus b. What about constants? On the left, I do have a constant term, that's 1, and that should be equal to the constants on the right, which is negative a plus 9b. So I get this system of equations to work with. Now I can get a substitution. So here, if I solve, for example, for a, you'd see that this shows that a is equal to negative b, or of course that negative a is equal to b. And if I plug into this other equation, we'd say, well, then that means that 1 is equal to minus b plus 9b, or that 1 is equal to 10b, or that b is equal to 1 over 10. And since a is just the opposite of b, a is negative b, that means a is negative 1/10. So then writing out our partial fractions that we had, and this was in the pink here, that's a over x plus 9, which is negative 1/10, over x plus 9, plus, and then we should have b over x minus 1. And b was 1/10 over x minus 1. And I would probably do this. I would factor out a 1/10. I don't want to leave it here in the numerator anyways. That looks terrible. Complex fraction. Ugh. So I bring out a 1/10, and I would say -1 over x plus 9 plus 1 over x minus 1. But for my own selfish reasons, I would also write these in the opposite order. I would just switch them around. No problem, right? I can say 1 over 10. I can say 1 over x minus 1 minus 1 over x plus 9. Now, what I really want to do is I want to be integrating with this. So I worked with the partial fraction decomposition, but my goal is, as part of the problem, to be integrating this. And I'll throw this notation in now after the fact, that I want to be integrating with respect to x. Now I can integrate with respect to x. So here 1/10 comes along as the coefficient, but then here I'm going to get natural log the absolute value of x minus 1 minus natural log absolute value of x plus 9. And just to clean this up a little bit, we would say, plus a constant c, but I am going to be working with a bounded integral. But just to clean this up a little bit further, I'm going to use a nice log property to write this as one log function. I can say the difference of two logs is the log of its quotient. So here I'll say 1/10 and then natural log of x minus 1 divided by x plus 9. And then, plus an arbitrary constant, but I won't need it since I have a bounded integral. So if I want to use this, I can return back to where I left off. This was sort of my detour that I took to work through all the partial fraction decomposition, but I had the limit as t goes to infinity. I've already integrated, but I still want to evaluate from 2 to t. So I can return back to what I was doing. Limit as t goes to infinity. And here I have 1 over 10, natural log absolute value of x minus 1 over x plus 9. And this should be from 2 to t. Now I want to plug in my upper bound and my lower bound and subtract in between. So we have limit as t goes to infinity, 1/10. I'm going to leave that factored out, but then here I'm going to plug in the upper bound. That's natural log absolute value of t minus 1 over t plus 9. And then minus, when I plug in 2, I get natural log absolute value of 2 minus 1 over 2 plus 9. And then I can try to work through some of the arithmetic for the part that doesn't have t's. So limit as t goes to infinity. I have 1/10 natural log absolute value of t minus 1 over t plus 9. And then minus, here I'm going to get natural log absolute value of 1 over 11. And I can work with a nice sort of log rule as well. Natural log of 1 over a is equal to negative natural log of a. So then in this case, the natural log of 1 over 11 is equal to negative natural log of 11. I don't really need the absolute value either, since I can see that this is a positive value. But this allows me to clean this up just a bit more. Say limit as t goes to infinity of 1 over 10. And here I have natural log of absolute value of t minus 1 over t plus 9. And then this is going to be plus natural log of 11. If you notice, I have this minus negative ln 11 is going to switch to plus. But I still have to work with the limit part, and I left all of this egregious space here on purpose, because what I want to do is I want to use a limit trick. There's a lot of ways you could manipulate this, but what I want to do is I want to divide everything by t, and that's really multiplying by 1 over t over 1 over t. But what's that going to do? It's going to divide every piece inside by t. You could also think of it sort of like a horizontal asymptote, if that's helpful. Lots of ways to think about it. Limit as t goes to infinity, 1 over 10. And then in parentheses, I have natural log absolute value of t divided by t is 1 minus 1 over t is just 1 over t, divided by t is going to give me 1, plus 9 times 1 over t is 9 over t, and then I still have this plus ln 11, sort of loitering, right? Now I can talk about the limit as t goes to infinity. And I can talk about this, I can sort of show work over here to the margin. If I want to show my work, we'll say the limit as t goes to infinity of 1 over t. Here as t grows without bound, 1 over t heads to 0. And then same, of course, limit as t goes to infinity of 9 divided by t also goes to 0. So now I can talk about what this does for a limit. So I don't have to write the limit anymore since I'm taking the limit. This is equal to 1 over 10, parentheses, natural log absolute value of 1 minus 0 over 1 plus 0, and then plus natural log of 11. And so this is just natural log of 1. If you remember, natural log of 1 is 0. This gives me 1 over 10, 0, plus natural log of 11. ln of 1 is 0. So then this leaves me with 1 over 10 times natural log of 11. And this is the value that we get. Since this is a finite value, remember what we said in the lecture video, our improper integral gave us a finite number. This means we have a convergent improper integral. The improper integral converges to this value 1 over 10 times natural log of 11. Let's take a look at just one more. I'm still feeling good. I hope you're still feeling good. We'll take a look at one more. The integral from 1 to infinity of natural log of x divided by x. First things first, I have to rewrite this as a limit. The limit as t goes to infinity of the integral from 1 to t of natural log of x divided by x dx. I can make my ln look a bit more convincing, so it doesn't quite look like an h, ln of x. But I want to talk about integrating here. Well, let me do that work in the margin. Notice, we'll get a different color, purple. If I want to integrate ln of x divided by x with respect to x, I need to use a substitution. We're going to let u be equal to natural log of x. The derivative du gives us 1 over x dx. So then I can replace all the pieces of this integral, and if it helps, you can even rewrite it a bit further, say the integral of ln of x times 1 over x dx. This cleans up very nicely. This gives me the integral of u du, which I can just integrate as a power function to get u squared over 2 plus some constant c, and then I can back substitute. We said u is ln of x, so we'd say ln of x quantity squared over 2 plus c. And that's just the work to integrate. I wanted to show that here to the side, and it involves the substitution method. But now I can use this result and go back and say, well, it's the limit as t goes to infinity of, and here I have natural log of x squared over 2. I don't need the constant since I have a bounded integral, and I'm bounded from 1 to t in this case. So I want to plug in the upper bound, plug in the lower bound, and subtract in that order. So we have the limit as t goes to infinity. When I plug in t for x, I get natural log of t squared over 2, minus, when I plug in 1 for x, I get natural log of 1 squared over 2. So we just got done saying in the previous example, important result, that natural log of 1 is equal to 0. So here I get 0 squared over 2, which is 0. So this whole second term is gone anyways, and we're left with the limit as t goes to infinity of natural log of t squared over 2. Let's talk about the log function. Let's talk about limits now. The limit as t goes to infinity for just regular natural log, what does this do? I think it can be sort of Hard to believe at first, but the natural logarithmic function is unbounded. It's not a fast-moving function necessarily, and if you've ever graphed it, it doesn't really seem like it's going too crazy, but it is unbounded, meaning if we just let it keep going and going and going, if nobody's watching it, if nobody's stopping it, it is going to get to infinity, but very slowly, sort of a tortoise and the hare kind of story. Right? If you've ever seen a graph of the natural logarithmic function, I'm sure you have, but you know I can't resist. Natural log of 1 is 0. It doesn't exist at 0 or for anything negative. It has this vertical asymptote. And then it's got this slow growth. It's not even that impressive. It's like watching paint dry. It's doing it though. And look, I already ran out of room. It doesn't even look like it really tried to get away from us, but it's going to keep going. And it is going to head to infinity. Mark my words. So what's going to happen here is I'm going to get something that's like infinity squared, which it doesn't really make sense to even say that. Since infinity is not a number, I can't really square it effectively. But I'm going to get something that heads to infinity. Squaring it doesn't change that. Dividing it by 2, infinity laughs at us when we try to do that. So this is going to give us, for the limit, it is going to give us infinity. It is non-finite then, so we'd say that this is divergent. We have a divergent improper integral. Hey, thank you so much. If you're still here, let me know in the comments below what you think of all of this stuff. Improper integrals, kind of crazy, huh? I want to say thanks for hanging out with me, taking a look at some of these problems. No matter where you are, what you're doing, remember to always keep learning, keep dreaming, and follow your heart. And I will see you next time for more of these problem sets. We're going to talk more calculus. We're going to have more cats interrupting us. It's going to be a really good time. All right, take care, and I'll see you next time.